Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're line dancing. So this is a way of resolving the ancient paradox of Achilles and the tortoise. If you haven't heard of that one, don't worry, just listen to this video for a few more seconds and you will. I also like to call this method of resolving the paradox the geometric series line dance. So the original formulation of the paradox is that a tortoise with running speed 1 mile per hour, probably wasn't the original number, but I'm just making numbers that work, challenges the mythical hero Achilles, running speed 100 miles per hour, to a 26-mile marathon race. The tortoise requests a 1 mile head start. The tortoise believes that as long as he never stops, he will win the race. Because first, Achilles, who starts out behind, must reach the tortoise's current position. By that point, the tortoise will have moved forward a tiny little bit. So Achilles will have to move to that new position. But by that point, the tortoise will have moved forward a tiny little bit. And so, according to the tortoise's logic, as long as he never stopped, however many rounds of that needed to happen, he'd always be ahead. However, the tortoise loses the race. As we know, it's possible. A fast runner can overtake the slow runner. So how does this work? How is this possible? That's the original formulation of the paradox. And so here's a graphical representation with badly drawn Achilles and badly drawn tortoise. They start off 1 mile apart. After some amount of time, Achilles is now where the tortoise was, and the tortoise has moved forward 1/100th of a mile. I decided not to draw countless little steps of Achilles getting immeasurably closer to the tortoise, but you'd be able to see that it would go from 1 mile to 100th of a mile to 1/10,000th of a mile. So the distance traveled would be 1 mile plus 100th of a mile plus a 10,000th of a mile, etc. Or the time that it would take would be 1/100th of an hour, right? Because Achilles is traveling at 100 miles an hour. So for Achilles to move 1 mile would be 100th of an hour. 100th of a mile would be 1/10,000th of an hour, etc., etc. In both of these cases, we're adding up infinitely many numbers, infinitely many positive numbers, yet we know that Achilles does not need to travel infinite distance nor take infinite time to catch up with the tortoise. Now, if you've ever had to solve a problem that deals with a fast object and a slow object and when one's going to pass the other, you know that this is a rather foolish way to go about doing it. Right? You know, there's a much more straightforward and more sensible way of doing this. We can say, all right, let R be the rate at which Achilles is getting on the tortoise. So Achilles is going 100 miles an hour, tortoise is going 1 mile an hour. The distance between them is shrinking by 99 miles an hour. X, the distance that needs to be traversed, or the distance by which the gap between them needs to be closed, that starting distance is 1 mile. And so the time, right, time equals distance divided by speed. So if the distance between them starts at 1 mile and is decreasing at 99 miles an hour, you'll get that after 1/99th of an hour, Achilles will catch up with the tortoise. Or Achilles needs to travel 100 miles an hour times 1/99 hours, right? Distance equals rate times time, which would get you 1 1/99th miles, or 100/99 miles. And this also makes sense. If you write out the fraction 1/99 in decimal form, it's 0.010101 repeating. Compare that to this repeating decimal we had here. 0.01 plus 0.0001 will get you 0.0101. Add one more round of that, you'll get another 0.01. So you'll get the fraction 1/99 in decimal form. Same with adding the 1 mile. You get 1 plus that much. Right? Hence, 1 1/99. So no matter how we approach it, it makes sense eventually. Since the same quantities derived by different means should be equal, right? We'll say that the time must be equal to 1/100 plus 1/10,000, etc., which also must be equal to 1/99. Therefore, we know that 1/100 plus 1/10,000 plus 1/1,000,000 must equal 1/99, or if that's continued on indefinitely. Similarly, 1 plus 1 over 100 plus 1 over 10,000 plus 1 over a million, etc., must equal 100 over 99. Which seems counterintuitive at first. On the one hand, you're adding up infinitely many positive numbers. But on the other hand, you're getting a fraction, right? A more straightforward version of this is if I were to take the decimals 3/10 plus 3/100 plus 3/1000 plus 3/10,000, right? That would get you 0.3 plus 0.03 plus 0.003. If I kept adding those up, I'd get 0.33333 repeating. We know that's equal to 1/3. It's the same idea, just different numbers. Now I'd like to introduce an alternate solution procedure. This one is more of the line dance approach. And the reason why I'm introducing this one when I've already introduced a solution procedure is that this line dance can actually be generalized to other problems, as I'll show later in this video. So let's start by assuming our rate of, so this R, that's going to be the rate at which, or the ratio between consecutive terms. So we'll look for both of these. Each term that's being added is 1/100th the previous term. So if I say 1 plus my ratio plus the square of my ratio plus the cube of my ratio, etc., let's set that equal to x. Right? So if my ratio is 1 over 100, this is the distance equation I have down here. I set this equal to some x. Well, I can multiply both sides by my ratio. And so the 1 becomes an r, the r becomes an r squared, the r squared becomes an r cubed, and then here's the line that I just slide everything over by 1 so that you match with the appropriate partner. So the 1 is left all alone, but these r's match, these r squareds match, these r cubes match. Then I can subtract the bottom equation from the top equation. Right? I can subtract r times x from both sides. So I have x minus rx here. Here, instead of saying 1 plus r squared plus r cubed, etc., minus rx, I can subtract anything equal to rx. I can subtract this r plus r squared plus r cubed, etc. So when I subtract them out, the r cancels with an r, the r squared cancels with an r squared, the r cubed cancels with an r cubed, the blah 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 cancels with the blah blah blah. Yes, I'm really allowed to just cancel the dots, as long as it's understood that it's the same thing inside those dots. And what I get is 1 equals x minus rx. Doing some algebra and solving for x, right? I can factor out a 1 minus r from here. I get x equals 1 over 1 minus r. Since r is 1/100th, I get x equals 1 over 1 minus 1/100th, which gets me that 100 over 99. Similarly, let's look at the time equation I had. Here, I didn't start with a 1. I started with my ratio, r. And then the next one's an r squared, and then the next one's an r cubed. So I do the same thing. I multiply by r. I also could divide by r if I felt like it. Either one will work. I tend to just go with whichever one fits better for making the algebra a little nicer. The algebra will work out just fine either way. You can sometimes avoid fractions by doing one rather than the other. If you do the other one, it doesn't matter. It's fine. It'll work. So I can say, so I do this, I get x equals r over 1 minus r. By the same procedure. Again, we move everything over, line dance, shift over to match your partner, subtract one from the other. I get r equals x minus rx, factor out the 1 minus r, and get x equals r over 1 minus r, which in this case, if r is 1 over 100, I'll get 1 over 100 over 99 over 100, that'll get me 1 over 99, same as I got before. Now let's talk about applying this approach to some cases. This comes up an awful lot in finance and theory of interest. Because if you're compounding interest year after year after year, then you'll get this ratio appearing. And that ratio will appear multiple times, right? You keep multiplying by that same ratio. So let's look at this application. Suppose you win a perpetual grant of $1,000 per year with first payment today. Assuming an interest rate of 3% per year, what is the purchasing power of the grant? Purchasing power, also called net present value, right? The idea that due to inflation, the $1,000 you'll get a year from now isn't worth quite the same amount as the $1,000 today. The $1,000 2 years from now won't be worth quite the same as the $1,000 a year from now. And so what we can say is x, this total amount, is equal to the 1,000 right now, plus 1,000 over 1.03, plus 1,000 times 1.03 squared, right, because it's 2 years of interest, or rather, so I say an interest rate, I meant inflation rate here. Purchasing power, strictly speaking, relies on inflation rather than interest. Those are pretty much interchangeable in most contexts. It's when you really get into it, inflation is one of the things that determines what the interest rate would be, and that you can decide, two people can decide to charge, or can decide on an agreement of whatever interest rate they deem fair. That doesn't automatically change what the inflation rate is. Typically, the lender will require that the interest rate is at least as high as the inflation rate, because not only does the lender need to actually receive something worth at least the same purchasing power as what was loaned out, but because the borrower has more control over when to pay back, and the lender is assuming a slight default risk, the lender will typically require that the borrower pay a greater interest rate than the inflation rate. But that's, so if you're studying for exam FM, you need to know that. Everybody else just looking at this because you need to know how to sum geometric series, you don't need to worry about that. Anyway, so you'll have x equals 1,000 plus 1,000 times 1 over 1.03 plus 1,000 times 1 over 1.03 squared, etc., etc. Now, I find it easier to multiply by 1.03 than divide by 1.03, especially if I'm going to be subtracting one from the other, right? So if I multiply everything by 1.03, the x becomes a 1.03x, the 1,000 becomes a 1030, the 1,000 over 1.03 becomes 1,000. The 1,000 over 1.03 squared becomes 1,000 over 1.03, etc., etc., etc. Now when I subtract this top equation from the bottom equation, I get 0.03x on the left side. The 1030 stays, and then everything else cancels out with its partner, right? You slide over to match the partner and cancel out. So I get 0.03x equals 1030. And so I go from this equation with infinitely many terms to an equation that's just this times this equals that. Divide through, I get x, the final purchasing power, equals $34,333.33. All right. Problem solved. Another application. Suppose you're making mortgage payments. You buy a house for $300,000. You make monthly payments of X for 30 years. That's 360 months. The bank charges interest at the rate of 0.5% per month. That's approximately 6% per year. As I mentioned, the interest rate tends to be a bit higher than the inflation rate. Solve for X. So solve for the payment that would be required. Notice that typically the bank isn't allowed to charge interest in that first month. Right? They're only allowed to charge if it's on anything late. So you'll say that as far as the bank is concerned, their interest, that X that you pay has to come directly out of the 300,000. Then each month of interest means that the amount paid is worth 0.5% less, right? So you divide by 1.005. Because one way that you could deal with interest, you could say, well, a delayed payment, right, a month later, has to be worth less. Now, if you're making 360 payments, the first one has 0 months of interest, the last one would have 359 months of interest. So you'll get x plus x over 1.005 plus blah, 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 and then the last one is x over 1.005 to the power 359, right? You have the 1.005 squared and the 1.005 cubed. I just didn't write all of those in there. So now you can do the same thing. Multiply by 1.005, slide everything over to match its partner. I know I didn't visually or graphically slide everything over quite visually, but you can imagine if I were to subtract one line from the other, everything cancels with its partner, except now this x times 1 over 1.005 to the 359, that's the one thing that doesn't have a partner to cancel with. So you're trying to subtract it out. Well, and I guess this 1.005x also doesn't. So this doesn't have anything subtracted from it. This term here gets subtracted, but there was nothing to subtract it from. All the other stuff cancels. So I get this 0.005 times 300,000, right? This 1.005 times 300,000 minus the original 300,000 is 0.005 times 300,000 equals 1.005x minus x times 1.005 to the 359. Which I can rewrite as x times 1.005 minus 1 over 1.005 to the 359. And I calculate out that x equals 0.005 times 300,000. Right? This is just algebra. You're solving for x. 0.05 times 300,000 divided by this factor right here, 1.05 minus 1 over 1.05 to the 359. And you crunch it out, you get monthly payments of $1,789.70. And typically that's the way mortgage agreements are. You'll pay the same amount every month so that you don't have to get out a calculator and figure out, if maybe you wanted to pay an amount that also grew with this 0.5% per month. But then you have to get out your calculator every single month. And they like to assume that you just want to know, I'm going to pay the same amount I paid the previous month. Just make it simple. So that's a way to figure out. Notice it's the same setup. Rather than saying, what's the final value if I knew the payment? If I know the total value and wanted to solve for the payment, I could do that too. Another thing we could do, what if we know the total amount and know the payment and wanted to solve for the amount of time? So this is a common loan repayment problem. You borrow $10,000 with a credit card that charges 1.5% interest per month. And there are reasons why specifically credit cards need to charge more interest. Notice this is per month, not per year. They need to charge more interest than other situations. Once you look into finance and beta values, it would make more sense. But this is not an exam IFM topic. The furthest I want to go with this is the regular exam FM stuff. For those of you non-actuaries who don't know what that means, don't worry about it. But one thing I'll point out is that you must pay at least $150 per month to decrease the balance, right? Because the interest on $10,000 would be $150 a month. Well, I suppose that's assuming you don't pay anything in the first month. So you gain that it accrues that extra $150. But you, starting in the first month, pay $300 a month. For how many months must you pay the balance? Include the smaller drop payment at the end as its own month. So what do I mean by that drop payment? Well, it's unlikely that if you're just paying some fixed amount, it's unlikely that you would end up at the end of some month with exactly $300 outstanding. You're more likely to get something where you have a little bit more than $300, you pay $300, you've got some small amount, and then that accrues 1.5% interest, and that amount would be less than $300. So you don't need to pay the full $300 for that last month, but that is called a drop payment. Another strategy is to pay more than $300 in 1 month. That's called a balloon payment. I'm assuming a drop payment here. Obviously, if you use a balloon payment instead, then you'll have one fewer month. With the method I'll show here, there's an easy way. You'll get a number that's between two whole numbers. If you want a drop payment, you round up. If you want a balloon payment, you round down. So, let's first pretend that you paid in perpetuity. So we want to figure out the total amount x that you're repaying. Notice here, x is not the number of months. Normally, x is the value I'm solving for. That's going to be n, the number of months, much later. But if I did pay in perpetuity, if I paid $300 every month, then I'd say x equals 300 times 1 plus 1 over 1.015 plus 1 over 1.015 squared, etc., etc., etc. do our line dance, multiply by 1.05, shift over, cancel with your partner. We ultimately get x equals 20,300. But the original loan amount was only 10,000, which means that 10,300 can go unpaid. So I would now say, imagine that I were to wait a number of months before starting to pay. I just didn't pay those first bunch of months. How many months would I wait in order to pay off those 10,300 that would go unpaid? And then I just reverse that, right? If instead saying, okay, now instead of those last infinity months, if those last months are the 10,300, then those will be the ones I don't pay, and I do pay the first bunch of months. And that should get me 10,000. So I notice that every time I wait and start paying a month later, the total amount gets divided by 1.015, because everything carries an extra month of interest. So how many months do I need to wait for this loan repayment to depreciate down to 10,300? So I have 20,300 times 1.015 to the negative n equals 10,300. Divide by 20,300, I got 1.015 to the negative n equals 10,300 over 20,300. And using properties of logs, right, log both sides, and use change of base formula, I end up with n equal 45.57. So if I wait for 45 months, that means if I were to wait for 45 months, then I would end up paying a little bit more than 10,300. So by reverse, if I pay for 45 months, I'll end up having covered a little bit less than 10,000. If I pay 46 months, I'll have covered a little bit more than 10,000. So that means I could either pay 300 for 45 months and then pay less than 300 in the 46th month, which is what the problem was asking, so we'd get an answer of 46. Or I could pay for 45 months, but then that last payment would have to be some amount more than 300. Not that much more. It would be between 300 and 600, but it would be a balloon payment. All right. There are a couple of other annuity structures that we can handle with this. The trick being, it would take more than one step of this line dance, so we could imagine a two-step line dance. Suppose we have an arithmetic annuity. An annuity is anything where you're making a deposit or a payment every year. Suppose you make a deposit of $1,000 now, $2,000 a year from now, $3,000 2 years from now, etc., and the last deposit would come 29 years from now, and that would end up being $30,000 if you follow the pattern. You deposit into an account. If that account earns 5% interest per year, what will the account value be in 30 years? So notice that first $1,000 earned 30 years of interest. The next $2,000 that you deposited earned 29 years of interest, all the way up to that last $30,000 only earning 1 year of interest. So our equation becomes this. The amount is 1,000 times 1.05 to the 30th, plus 2,000 times 1.05 to the 29th, blah, 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 blah. And the last line is 30,000 times 1.05. We do the line dance twice. Multiply by 1.05. So 1.05x equals everything with one additional power of 1.05 on it. Subtract the corresponding parts. We get 0.05x equals this 1,000 times 1.05 doesn't cancel with anything. This 2,000 times 1.05 to the 30 gets subtracted, so we subtract from that a 1,000 times 1.05 to the 30. There's an invisible 3,000 times 1.05 to the 29, which cancels with this 2,000 times 1.05 to the 29, so we get another 1,000 here. We get 1,000s for every power of 1.05, minus this one spare one without a dance partner. This minus 30,000 times 1.05 just gets subtracted. Now, typically, we want something with a small number of terms. This still has a large number of terms. But if we do the line dance a second time, shift over by multiply by 1.05, shift over, cancel with the dance partners, we get a 1,000 times 1.05 to the 32, that cancels with nobody. No other 32nd power dance partner here. The 31st power dance partners cancel. The 30th, etc., etc., etc. Now, we end up with 3 leftover terms. This minus 30,000 to the times 1.05 to the second. I have a typo. Sorry about that. Realized there was a typo and had to fix it. So we crunch all these numbers together and we get that x must equal $834,976.59. Just subtract out. Right? We know that if we do the second step of the line dance, we now have only 3 terms. That can be calculated relatively painlessly, and then you just divide by this 0.05 squared. Lastly, there's one more annuity structure that I've heard called rainbow annuities, or sometimes triangular annuities. The idea is that the payments start increasing and then start decreasing. Suppose you're awarded the following 9 payments: $1,000 now, $2,000 in 1 year, $3,000 in 2 years, $4,000 in 3 years, $5,000 in 4 years, and then starts going down: $4,000 in 5 years, $3,000 in 6 years, $2,000 in 7 years, and $1,000 in 8 years. Assuming a 3% inflation rate, what's the present value of the payments? So we do another 2-step line dance. We just write out this x equals, and I've got this all written out here. 1, 2, 3, 4, 5, down to 4, 3, 2, 1. For the first step, I multiply by 1.03. So I've got the 1030 and then 2, 3, 4, 5, 4, 3, 2, 1. Again, with one lower power of 1.03. I take the difference, 0.03x equals 1030, and now when I subtract, I have a 2,000 minus a 1,000 is a 1,000. 3,000 over 1.03 minus 2,000 over 1.03 gets me a 1,000. I have these positive 1,000s here. Then when I start looking at the 1.03 to the 4th term, I have a 4,000 minus a 5,000. That gets me a minus 1,000. Then other minus 1,000s all throughout. So I have pluses and minuses. Now, while I did write these all out individually, it still would be a pain to crunch these out one at a time. And we can see the pattern. We can see what the pattern is going to be. And if we had, maybe it wasn't 9 payments, maybe if it was 19 payments, so it goes 1 to 10 down to 1. Then we do the second step of the line dance, right? And we should have only a few terms to add. So in our second step, I've just rewritten the last line. We multiply by 1.03 again. So this 1030 becomes 1060.90. Then you get a 1030, then 1,000. And we get these pluses and these minuses. When I subtract one from the other, right, everything cancels with its dancing partner. The 1060.90 never goes away. Bunch of these go away, but then this minus 1,000 over 1.03 cubed, with this, well, I subtract this 1,000 over 1.03 cubed, it becomes a minus 2,000 over 1.03 cubed. And then everything else has something to cancel with except for this one. This guy doesn't have a dance partner to cancel with, so you subtract the negative, you get a plus. And if I factor out 1.03 squared from this, I get 1,000 minus, I factor out the 1.03 and the 1,000, I get a 1 minus 2 over 1.03 to the 5 plus 1 over 1.03 to the 10th. That last term, that 1, negative 2, 1, you'll notice that's an a minus b quantity squared term. So this becomes 1 minus 1.03 to the 5th squared. If you FOIL that out and multiply it all the way through, you get that these are the same. Which gets you x equals 1 over 0.03 squared times 1.03 squared times 1,000 times 1 minus 1.03 to the 5 squared. You may notice that that happens to be the value of a 5-year level payment $1,000 annuity. So there's that formula that rainbow annuity equals square of level payment annuity. Anyway, as always, if you like the way I explain things and want to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.